I'll start at 3:35. Okay. So C34. Okay, it's 3:35. Time to start. Share my screen. This is weird. Start recording. Share screen. Get my DPLL-T slides. Go to full screen. Okay, so we'll start. So last time, in the last class, we saw the core solver, that is a solver for combination of theories, okay, which was a decision procedure for conjunction of formulas drawn from several theories put together, but conjunctions, okay? And we saw that how to decide conjunctive fragment of union of theories by propagating equalities. And we saw that that was decidable under certain restrictions. Okay, so today I will describe the extension of DPLL to DPLL-T, which is a decision procedure for deciding arbitrary propositional combinations of atomic formulas drawn from mixed union of theories. Okay, and you will see that this DPLL-T will is very much like DPLL, except that it talks to the core solver, that is the theory combined theory solver, to do to decide formulas for arbitrary composition of things. Okay, so first let me get this just to motivate you. So let's suppose you have a formula. So this formula now is formula over the theory of equalities, okay, or variables. There are no function symbols in this case, but this is not the conjunctive fragment. This is an arbitrary proposition. It has an arbitrary propositional structure, non-conjunctive structure. Okay. So what does it mean to decide the satisfiability of this formula? So whatever satisfying instance will have to satisfy the propositional structure, there's propositional skeletal structure inherent in the formula, as well as it has to preserve the semantics of all the theories combined. In this case, there's only the atomic formulas are drawn from the UEF theory. In any case, in general, it has to preserve that thing. So one way you could do this is by taking a Boolean abstraction of this formula. Okay? So that is which is obtained by replacing every atomic formula in this thing by an arbitrary propositional variable. So here x is equal to y, y is equal to z, and all those things are replaced by separate Boolean variables. Okay? Every atomic formula is replaced by a Boolean variable. Now, so this is what I call as a Boolean abstraction of the original formula. So this T to B of F is an over approximation of the original formula. Therefore, if, no, sorry, what's happening? Yeah, so if the original formula, so what does it mean to be an over approximation? Because these things are replaced by arbitrary Boolean variables. So if the original formula is valid, then if the abstraction, Boolean abstraction is valid, then the original formula is valid as well. In other words, if it is unsat, then the original formula is also unsat. Okay, but if it is not unsat, but if it is but get a satisfying instance of this formula, then you will have to check. Of course, any satisfying instance has to satisfy this formula, and additionally, it has to satisfy the theory constraints. So one way to do is to get a satisfying instance of this formula. For example, one way to satisfy this is to make B1 to be true, B2 to be true, and B3 to be false. That is one way to do it. And that's satisfying, and then you'll have to check if that preserves the theory semantics. So in this case, if you choose that satisfying instance, you will notice that x is equal to y and B2 is y is equal to z. And because the transitivity property there infers x is equal to z, that satisfying instance, although it's satisfying the propositional structure, is not preserving the theory semantics. So that cannot be a satisfying instance of the thing. So for each satisfying instance here, once you obtain that you could obtain by using DPLL, and then you will check if each satisfying instance will be a conjunction, correct? A conjunction because each of them is can be represented as a conjunction of the original theory, and so you can use the theory solver, the combined theory solver, on that to check if it is satisfiable or not. Okay, so that is the basic idea that is used. Although we will go through several optimizations of that thing. Is that clear? Yeah. So we now go to the full screen mode. So that is pretty much what you have. So you will have the what it takes is that is the simplest, the basic DPLL-T framework. So you will have a DPLL thing on which you get a satisfying instance of the Boolean abstraction. And then then it will be mu1 and mu2, they are satisfying instances. And after that, you will check if it is using a combined theory solver, if that is acceptable or not. Okay. Now, of course, you can have a more, this is like invoking the combined theory solver as a black box. Okay. And we'll see that a closer integration will be a lot more efficient for various reasons, and how exactly that integration is done is what will be the framework of DPLL-T. Okay. So there are two ways. Either you can use it as a black box, that's what I refer to as offline, or online, which is a bit more closely integrated into the CDCL DPLL structure of the thing. So the offline one, as I illustrated on that example, is described here. It works as follows. So you first obtain the Boolean abstraction, the propositional abstraction of the original formula, and then you invoke a CDCL based DPLL, the CDCL SAT solver on it, and yeah, so, and that will give a result with a satisfying instance. If that is unsatisfiable, you can return unsat. Otherwise, you will have to check using the combined theory solver. You then take the original formula. You go back to the original formula with the satisfying instance also added, and check if that is satisfiable. If that is satisfiable, then you return SAT. If not, of course, there could be another satisfying instance of the propositional abstraction, which you'll have to try. Therefore, you block you go back to you block that propositional assignment, and you try to get another satisfying instance using CDCL. Okay, so that is that's what you will have to do if you have to use this CDCL as a black box. So any questions here? Is it clear so far? Okay, so no questions. I'll move on. Yeah, so since we're using SAT solvers, we will have to get the original formula in CNF. So T2B computes a Boolean abstraction of phi by replacing every atom in phi with a fresh Boolean variable. And B to T computes the reverse, the inverse of T to B, and that's what. And mu P is a partial assignment to the proposition variable here. Okay. And what you're blocking here is usually called the theory conflict, because it is indeed a satisfying assignment for the Boolean structure, but it does not obey the theory rules, and so it is a theory conflict clause. Okay? And of course, this when you solve the propositional abstraction of the formula, that will involve all the details that you had of generating partial assignments, BCP, followed by conflict clauses, Boolean conflict clauses that are generated, and so on. But the new kind of conflict clauses that you're generating are due to theory conflicts here, which need to be blocked as well. Correct. So yeah, so for every unique theory atom, you will have to replace that by a Boolean variable, and so this is a recursive way of doing it, and B2TB is the inverse, as I indicated. So let's try. Yeah. So this is just to show. We've already seen this. This is just to illustrate T to B and B to T, and that's what that thing is. So So let's see how this thing works on that, on a simple example, okay? So this is sound to do this is because, as I pointed out, phi p is an over approximation, and therefore, yeah. So CDCL will never return unsat for SAT formulas, and it only returns SAT when mu p, that is, it satisfies both the propositional structure and is also consistent with the theory axioms. And why should this terminate? Because there are only finitely many satisfying assignments to the Boolean abstraction. There's only, the formula has only finitely many atomic formulas from the theory. And every time you go back to the theory solver, you go into the theory solver, you get a different assignment, and therefore this will terminate. Okay? And so this is indeed a sound and complete decision procedure for thing. Okay, so here is how it works. So you first get the Boolean abstraction. Then so you get a satisfying assignment B1, B2, B3, and since yes, okay, and that you check. So in this case, that is one possible assignment. So obviously that doesn't work. In this case, the original formula itself is unsatisfiable, but still to illustrate, how it works. So then you get this, and then you block that assignment by taking the adding the negated negation of this as a clause. Try to run CDCL again to get another satisfying assignment, and block that, and so on. So then you have tried all of it, and then you will get unsat. So because the CDCL itself, when it gives unsat, then you return unsat. Okay. So you probably or have already guessed this is not the most efficient way of doing it, and I will list some of the reasons here. Here you're blocking one assignment at a time, and also in some cases even, and the other thing is you're only shipping full assignments to the solver. So maybe even a partial assignment might be inconsistent with respect to the theory. So you may, detecting that early on, might help you in eliminating some partial assignments. So there all these things are what you can't do when you have when you invoke the CDCL as a black box, between the thing, and that's what, yeah. So the theory, the first thing is it's maybe too weak, so you could try and get a more a general theory conflict clause to block. And one way, a simple way to do that is to get the minimal unsatisfied core of that assignment. Now, in this case, if you see the first assignment, satisfying assignment, which does not preserve the theory, is B1, B2, and B3. So, and when you refine that, you will get x1 equal to 1, and x2 is equal to x is equal to 3. So both x1 is equal to 1 and x is equal to 2, as well as x is equal to 1 and x is equal to 3. Both of them are, so they are both separately unsatisfiable core, and therefore what you can do is, instead of going through all these things, once you get this assignment, you can then get along with the, if the theory solver is able to give you an unsatisfiable core, then you can use that instead to block it, okay? To block multiple possible multiple assignments. Then you will be able to save some of the you may be able to get faster convergence. A single unsatisfiable core may be able to block several different unsatisfying assignments. So that is one, but still, as I pointed out, disadvantage of using it as a black box is that you will have to wait for full set of assignment. For example, in this case, even partial assignment is also inconsistent, and therefore, if you can not wait till you get a full assignment and even partial assignments, but that will require, of course, for you to integrate CDCL with the theory solver more intimately. Okay, that is one. The other thing is, I'll go back to which is called theory propagation, okay, which you can do. So take this example, for instance. Now, once you got this assignment, B1, B2, that's a partial assignment for the propositional structure. And if you saw the Boolean, the theory refinement, that is x is equal to y and y is equal to z. Now, you know that as per the theory rules, if x is equal to y and y is equal to z, you know that x has to be equal to z because of the transitivity rule. So if you could, based on partial assignments itself, if you can derive consequences, theory consequences of implied by those partial assignments. In this case, for example, you could add x is equal to y and y is equal to z implies x is equal to z to your original clause, and then you will be preventing similar conflicts to get later on. And this you could extend to any general implications of your partial assignment in the theory, okay, in the underlying theory. So that if you can use theory propagation, that is, if you can propagate the consequence of the partial assignments, and then add to your original clause certain valid consequences of your partial assignment, then you may inhibit the several other Boolean assignments at the propositional level, which could conflict with the theory much sooner than you would be able to do in this thing. So all these things is what it's suggesting is rather than make your thing interact as the two components here, CDCL and the theory solver as black box, it's better to integrate them, and that's what gives rise to the DPLL-T framework. Okay, so recall that this was what you had. Okay, the original thing. Okay, you recall that DPLL was this. Okay, on the right side. Okay, and you see that this structure is very similar to that, except for there is, instead of decide, there is something called T decide, theory decide, which kind of combines the BCP and decide. Okay, but pretty much has the thing. So this is a version of an algorithm that integrates the T solver more closely with the CDCL structure. And the T solver now is embedded inside T decide. And this we will is what we will study. Okay. So any questions so far? Okay. Yeah. So there is some pre-processing thing that that happens here, where you could maybe propagate some unit clauses, or eliminate certain redundancy at the theory level, and maybe you could do that. So for now, let's not ignore the first the first part. Okay. So what you will do, you will start, and that may maybe there are by looking at those certain pre-processing, you may come to the conclusion that certain assignments have to be done for it to be true. In this case, maybe you can start with an assignment based on that pre-processing step, but nonetheless, your starting point is, so for our purposes, let's now assume that the initial mu p is empty. Okay. Yeah, these are some of the kinds of things. Maybe you can eliminate some dual operators, etc., exploit associativity and things that you could do at the theory specific structure for optimization. Okay. So let's get to start from this point here, where you first, as a first step, take the Boolean abstraction of the original formula. Okay. And then I'm going to describe what will happen next. So T decide, this is very similar to decide in CDCL. So what does decide in CDCL does? It selects an unassigned literal here in the Boolean abstraction, and adds that to your partial assignment. Okay. And yeah, that's pretty much okay. T decide does. It's similar to that. And then you go and then do T deduce. Okay, so you said even every time you make a partial assignment at the Boolean level, you do this. Okay, you invoke the theory solver. That's what is what I mean by closer integration. So what does T deduce do? It does several things, okay, so which is listed here. It applies the BCP to the the original BCP to the propositional structure, given the partial assignment, because now as soon as you make a decision, you have a partial assignment, until one of the following things are possible. As part of that, you will see, in addition to BCP, it also invokes the T solver. So the T solver invocation happens inside this, that is integrated with the Boolean constraint propagation part of CDCL. Okay, so so when that is done, what can happen? The BCP, if it's propagated, mu p propositionally violates. You can get a conflict at the Boolean structure level itself. Then that is also a conflict for the combined thing. Or what can happen due to BCP? You could you might end up propositionally satisfying the propositional abstraction phi p, in which case, as we saw before, you will have to make sure that it is consistent with the theory rules, and therefore you have to invoke. In that case, it invokes the T solver on the refined version, on B to T of the partial assignment, mu p. So earlier in the black box approach, we were getting the complete satisfying assignment doing it. Here, we are invoking the T solver eagerly, okay? even on a partial assignment. But of course, you'll have to do that after refining, because the T solver has to work on the theory atomic formulas. As I said, every partial assignment is a conjunctive, lies within the conjunctive fragment. That's why you can use the original T solver. Now, if that returns SAT, then even your partial assignment is indeed a satisfying assignment, and therefore you can return SAT. Okay, if T solver, the result of invocation of T solver results in a conflict, then it is indeed a conflict. Okay, then you declare it as a conflict. Now, it is not unsat yet, because you only got a partial assignment, and therefore you'll have to try and get a different assignment. That's why that will also a kind of conflict. This kind of conflict is what is called a theory conflict. Okay, this was not happening in pure prepositional thing. So the first case is prepositional conflict. Here, even when you have a prepositional assignment, you're getting a theory conflict. So you have to make note of that, okay? And then analyze that conflict, and then resolve, figure out how to block it and resolve it. The other possibility outcome of doing BCP is that you don't get a conflict. You may end up just at the propositional level, just end up with a bunch of unresolved clauses. Okay. In that case, the partial assignment, if on the partial assignment, then even in that case, you invoke the T solver, okay, by taking the refinement of the current partial assignment. If that returns conflict, of course, if even that partial assignment, refined version of the partial assignment is conflict, then of course, you won't, any extension of that will not work for you, and therefore you will, return T solver and returns a conflict if the T solver returns unsat on that partial assignment. If it is not, if it does not return unsat, then you can actually do theory propagation. Okay, I mean, in any case, on this partial assignment, like I showed, before, when you have x is equal to y and y is equal to z, you can also propagate some valid inferences based on this propositional. Inferred by the theory, so that you could add them as valid consequences, and that is something new that is happening here, which is called theory propagation. The first thing where you get an unsat and you go back, that is called early pruning. It's called early pruning because you're pruning out certain satisfying assignments which are not consistent with the theory. Okay, and for that satisfying assignment, you can also infer, if you can infer some useful literals, theory literals, then you can, as a result of theory propagation, you can add them as well, so that they can be used in the BCP at the propositional level later on. These are the things. So lots of things happen inside TDEDUs in addition to the BCP. As a result of the outcome of BCP, those things happen. After that, the rest of the thing is pretty much, is the same as CDCL. So so if the result of TDEDUs is SAT, then you return SAT. If it is conflict, then you will analyze that conflict at the propositional level, and then you use the same kind of thing. Okay, so that's okay. So here are the details. So it kind of extends. If the conflict is caused purely by BCP failure, it returns the same level and conflict clause. If the conflict clause is caused by a theory failure, okay, as a result of T solver giving unsat, then that will produce a new kind of conflict clause. And this is called mixed Boolean and theory conflict clauses. So this is an additional class of conflict clauses that get generated as a result of passing partial assignments to the theory solver. Okay, so that's what. So the analyzed conflict adds these two, an additional class of conflicts arising out of theory solving as well. Yeah, so here it is pretty much similar to CDCL. It adds the learned clauses. And then this new version, because it can add certain theory conflict, mixed Boolean theory conflict as well, it's called T-learning, and it backtracks to the B level by undoing, similar to before. You can use non-chronological backtracking. Okay, so that is how this close integration happens. Okay. Yeah, do you have any questions? If you have any kind of general questions here, please ask me, or you can hold on until I show you a detailed example as to how it works. Any questions? I hope you understand why this closer integration helps you. Okay, and that is what that you should, and one of the key takeaways should be. Okay, because you're doing these things instead of invoking T-solver at the very end. You're invoking after every partial assignments. And the other thing is you're also learning from the theory conflicts that you get. Number 3, theory propagation also happens. Even if a partial assignment is not conflicting with the theory rules, you try to get some useful, valid consequences of the partial assignments that you have made, and that is also added to your original set of clauses because they're valid consequences of your thing. Okay, so let's go to an example. So what is shown here on the left in black are original clauses. Here we have a set of 7 clauses. It is just these clauses drawn. Some of the atomic formulas are drawn from the theory of linear inequalities over arithmetic. So it could be real or numbers. I mean, say it is integers. And it also has some propositional variables. Okay, I'm using only one theory here for illustration, but I mean, you could extend this for arbitrary theories. Okay, so A1 here is just a propositional variable, and this is a atomic. Now, what is shown in blue on the right side is the propositional abstraction. Okay, that you get by replacing every atomic theory formula with a new propositional variable. So that's what is done here. So what is shown in blue is the propositional abstraction. And the propositional level of CDCL operates on the clauses shown in blue. So you start by, so suppose you, by making certain decisions, because none of the clauses is unit. There's no BCP, is not needed here. So you'll have to make a decision. Let's suppose that we make decision, not B5 at level 1. That will have some simplification, but does not require any BCP. Similarly, B8 at 2 that will make 7 go away, not B5 at 1, makes 4, clause 4 go away, B6 at 3 makes clause 6 go away, okay? So you still, since you're still left with some unresolved clauses, you will be able to make the next decision, making not B1 at 4. Well, so at this level, see, after each of these decisions, normal CDCL will just go on making decisions. So here, one difference is theory propagation. So after you make not B1, at each of those points, you will have to see as a result, each of these decisions really mean making certain conjunction decision on conjunction of atomic literals. You'll have to see if you could propagate some consequences of this theory. Now, here is the first instance of what illustration of what I mean by theory propagation. Okay, so once you make this decision, okay, now as a result of not B1 and not B5, interpreted as a conjunction of linear inequalities over real, implies a certain decision. This is not an implied decision due to BCP, okay? Due to BCP, nothing gets inferred even at this level. But not B5 and not B1, where B5 is whatever, okay? When B5 is 3x1 minus x3, and B1 is 2x2 minus x3. That causes at the theory level certain implications. So theory propagation involves getting those things as well. So in this case, if you look at those two things closely, this is what the decision that you made was, not BF and not B1, okay? So if you look at the refinement of not BF and not B1, what you get is this. 3x1 minus x3 is greater than 6. That is the negation of this. And 2x2 minus x3 is less than or equal to that. So that, based on linear theory of inequalities, implies the negation of this, okay? That it actually, you can see that this one, when you plug it in and so on, see it'll, this cannot be true, okay? 3x1 minus 2x2 has to be greater than or equal to 4, assuming that it is on integers. And therefore, that infers B3. This is what theory propagation is, okay? We can ask, how do you, of course, you could do this theory propagation every time you make a decision on a prepositional variable which is denotes a theory atomic formula. But what are the consequences you will be looking for, you may ask, okay? Because there are so many consequences of those things, but you can limit that search to consequences that are, of literals that appear in your original, clause, and therefore that way you could, you could limit. So this is what theory propagation is. This is propagating literals and adding them into the BCP process as a result of doing that. And additionally, since that is a valid consequence of this, you can even add these kinds of clauses, okay, to it. These are not conflict clauses. These are actually clauses that are valid as a result of certain decisions. So here, what you're saying is not B5 and not B1 implies not B3, okay, which is valid, okay, as in general, and therefore you can actually add them, okay, and this can be very useful later on when you backtrack and do things and then come back to make the same decisions. So these are not conflict clauses. These are something that are obtained as valid consequences of decisions made here. So this is one significant difference here. Okay, so is that clear? So you have any questions here? So key to understand is this is not arising due to a theory conflict. Okay, this is propagating consequences of your theory, which are also consequences of your partial decisions in terms of the theory. Now BCP kicks in as a result of this, adding this theory consequence clause. Okay, so the moment not B3 is added. Clause 5 implies A1. That kicks off a chain. Then C3 can also be plugged into, I'm sorry, this literal can be plugged into C3 to get A2. And you plug that into, and that into C2 will give you B2. Let me go back to. Now, this results in a conflict. Okay, once you get B2, not B5, and B8. Now, this is a real theory conflict, okay? Because if you now refine this clause, if you look at not B5 and B2 and B8, which if you look at a closer look at that, that is this one, okay? So that is cannot be, that's a conflict because it cannot be, it is not satisfiable as per linear arithmetic, arithmetic inequality consequences. So this is what not B5, B8, and B2 represent. So that will imply that 3 times x1 minus 5 must be greater than 10, while at the same time x1 minus 5 must be less than or equal to 1, which is not possible. Okay, and this you get as soon as you make certain, as BCP once it ends. Okay, so here was a case. If that itself gives a conflict, then that gives a Boolean conflict. It will be handled as before. But here, even though you got a satisfying assignment after BCP, but that need to be checked to see if it obeys theory rules, and that's what is being done here. And in this case, when you invoke the T-solver on it, as I showed in the thing, so that results in a conflict. So this will also be some clauses. So when it is now, when you take it back into the Boolean level, this results in a theory. It results in a theory conflict, and you add that. And this is what I refer to in the algorithm as mixed Boolean theory conflict. Okay, because the source, the cause of this conflict is due to invocation of T-solver, but it is being added as a conflict clause, as a Boolean conflict clause into the CDCL, part of it. Okay, so as opposed to if you got a conflict by the CDCL itself at the Boolean level, that will be the more traditional Boolean conflict. To distinguish that from that, this is called mixed Boolean theory conflict. Now here, which conflict clause to add? You could analyze this thing as before in CDCL, by using implication graphs and doing it. And if you pick the conflict clause, that has the first UIP, that is the UIP, unique implication point, closest to this. This is what you will need to add. Now you can also add sometimes in addition to that, sometimes, okay, because they, some SMT solvers. So if the SAT solver, this is the only one that will be added. okay? If it was a pure SAT solver. Here, there is some reason to also add sometimes if your theory propagated literal, a clause that contains the theory propagated literal as the sole UIP, that sometimes you also add that, okay? Because, I mean, so here that happens to be the, one containing the original thing. So that's a variation for variant of the thing. So you can also add this, and then you will backtrack, do chronological backtracking. That is, you backtrack to the highest level other than the current level, which in this case is 4. So you would backtrack to B8, okay? Once you backtrack, you will see that you will not even get the decision that made you get not B3. Even that will not happen because it flips. As a matter of fact, here the clause 9 itself will also make you flip that, because this is indeed B2 indeed is a UIP. But as I told you, because B3 is a theory propagated one. Sometimes even adding that clause seems to be a useful, an additional conflict clause. Okay. So, is any questions here? I know there are a lot of details. Okay. So you should be asking questions if indeed.
So why are we adding clause number 10, the last one?
Yeah, as I said, the first one was added to theory propagation. Normally, you would be adding only this. As I told you, you're adding this to what I was saying was that you could also, I mean, if you want to prevent B3 itself, okay, directly, the theory, that thing, then you can go all the way back to this UIP, and then you can add the UIP with the decision, okay, that created the theory propagated literal, okay. I'm showing that only to say that sometimes they also add that, so that you can immediately prevent the decision, prevent the decision, which in this case is not of B1, that created that theory propagated literal, okay, which is what led to the conflict, okay. So, in this case, you would get that decision, but you will have to do a BCP, okay? If you added that, see, even after adding, in this case, after adding this, if you backtracked to this level, it will flip the decision of B2, okay? But it may not flip the decision of B1, which is really causing this. It turns out in this case, B2 will flip that decision. But if you want to make sure that you want a clause that blocking clause, a conflict clause that will prevent the theory propagated thing itself, okay, then you will have to go back further into the thing to block the production of the theory propagated literal. So that's why sometimes they say, oh, in addition to blocking this, you also go back and then see what the some UIP clause, if that means you have to go back all the way, so be it, that will directly block this implied theory literal, okay? Theory propagated literal, that's all.
So if the theory propagated literal was not blocked, then in like future iterations, we would have to have more calls to the theory solver just to
That's correct.
generate those
Yes.
implications, right?
Yeah. Yeah.
And we're trying to sort of avoid that.
Yeah.
Okay.
Yeah. But yes, you're right. In this particular example, it so happens that it'll block that automatically as well, but it may not. Okay. So that is the reason, because here at the proposition level, you don't know which is theory propagated, which is not. Was obtained due to theory propagation and not. So as far as this the analyzed conflict of CDCL. So here, you can add certain additional conflict clauses that directly prevent those theory propagating. You're exactly right. So that later calls to theory solvers can be reduced. Yeah. Yeah, so that's the result. So here it will immediately flip that, okay? Whereas this clause 9 will not flip that that decision, okay? And therefore you may create that the same theory propagated literal, which is the source of this conflict. Okay, so that's the thing. Okay, so yeah, correct. So that is yeah. There is another version which I'm not sure if I will. Maybe next time I will. I mean, I will get to that because I want to reserve some time for project discussion. Today I want to have something. So there is another level, an even more intimate level of integration, which is actually discussed in this book. By the way, this I'm following once again the decision procedure chapter 3 in this thing. So there is some yeah, difference in the pictures. Okay, so maybe it will be very clear. So some of the pictures that I'm using are slightly different. Okay, so maybe I'll point that thing out. Yeah. So what is T decide? I mean, if you end up referring to that chapter, I'm sorry, T deduce is this entire thing here. BCP, deduction, and add clauses. That entire 3 components combined into one is what T deduce is. Okay. So you do BCP. If it results in conflict, it's one. Every time you do a BCP, you propagate something, you can call the theory conflict, and then you add clause and then go to BCP. Okay, so even on within the BCP, as you propagate the literals, after each generation of each Boolean literal, you will propagate that partial implied set of partial implied literals, partial set of implied literals to deduction, and then you generate clauses and so on. Okay, and that's kind of the difference. So what I was talking about was, this is something that is not in the book, and I'm not sure if I'll cover that or not, but there is also further, some people believe that there is, you see, here we have not gone into the T solver. What we have done when we went from offline to online was integrated the T solver into the structure of CDCL, DPLL. We did not break into the T solver itself. As you know, the T solver as you saw in the last class, when it combines two or more theory solvers, it propagates these equalities or disjunction of equalities. If it were a non-convex theory, one of the theories were non-convex, correct? So, you could integrate it so that this EIJ, as you propagate each of these individual theory solvers, are kind of integrated. That theory propagation itself can be maybe lifted to the level of CDCL, and then if there seems to be some value in inferring, using these equality propagated inferences, which are all inferences of these theories in, precluding learning, doing some more learning as based on these equality propagated literals. And that is something that is discussed in this book, in this paper. Okay, that is not in the book, and time permitting, if I think I might, I'll discuss that. But what I want to point out is that this is all degrees of laziness. Okay, the offline version is the most eager version. Okay, so here you kind of delay, so you decide lazily, okay, and then you invoke T-solver. Here combine, and here individual T-solver. So you can also, do this kind of integration, which in some cases apparently might help you get better results. Okay, so I want to stop here. Okay, and I entertain any questions you may have. On DPLL-T? Okay. There are no questions.
So
then
I had just one.
Yeah.
Yes, are we backtracking for so in the brief overview you stated at the beginning, you said that we were sort of backtracking differently for different kinds of conflicts. Is that why? What is the motivation behind that?
No, the backtracking is the same. Okay.
Oh, okay.
The backtracking has no difference. It's only what kind of conflict clauses that you add. Okay. There are more additional conflict clauses here. Once you add that, then you backtrack. Based on, you look at all the conflict clauses that are added, and you use the same strategy as before. If you were to use non-chronological backtracking, then you look at all the conflict clauses and backtrack to the latest level among those conflict clauses other than the current level, okay? Which in this case happen to be the same. So the number of conflict clauses that you add is one of the heuristics. It is to go back and then try to add conflict clauses that prevent the theory propagated literals that you generate during VCP. During T-deduce, correct. That answers the question. That is, the backtrack is just like...
It is the same. It's just guided by the more clauses, basically.
Yeah, it has more clauses, correct. Yeah, but the theory propagated clauses, the valid consequences, that is not considered as conflict clauses, okay? Because it's the conflict clauses are the original Boolean ones that generated the purely Boolean level, or due to theory conflicts, yeah?
But the theory validated, like the implication clauses, if you will, that come from the theory solver, they are also carried over to later iterations as well, though, right?
They are carried to later iteration. Everything that you add stays there, okay? Because they are all valid consequences.
Okay.
Even the theory one, can be interpreted as a result of this implies that. Now, as a result of making these decisions,
Right.
it implies that. That is always true. That is true there as well as here. I mean, only the reason is that it is not just due to propositional, but also due to some propagation of theory rules. That's all.
Even these might prevent future like theory solver calls.
Correct. Yeah. This can be used in what? The theory.
So
No,
as in we don't have to specifically derive this particular implication anymore using a call to the theory solver, since we're already adding it in. Like BCP itself will give us the implications coming from this particular theory
correct.
solver.
This one, so there's a difference between, sorry, 9 and 2 are conflicts, okay, obtained by looking at the implication graph, but not this one though, not clause 8. Okay, so that is obtained purely by, see, B5 and not B5 and not B1 did not cause any conflict, okay? It just happened to imply not B3.
Right.
Yeah, but that will also stay. That will also stay at the level of, yeah, that will be added as theory propagated clauses to the original formula. But they'll only be used during BCP at the Boolean level. They'll not be used at the theory level, for theory solving.
Yes.
So these,
Yeah, okay.
when all these conflicts preventing this can also prevent certain decisions, right? So which you from making, later on, if you backtrack and then if you're making B5 and B1, then you're directly preventing not B3. This one is preventing B1 itself in a different way, okay? Because if you made B1 independently, okay, if you made B5 and B1, then it'll say, oh, not B3, so that you don't need to, like you pointed out, you don't need to call the theory solver to check that again, okay? To derive that, or to even to derive that particular clause, okay? See, because checking, using the T solver to check whether a partial assignment is satisfiable, unsatisfiable is less hard than deriving these implications due to valid implications, okay? So therefore, so there I'm relying on the theory solver being able to just like, derive these consequences. And there is a little bit of hunting around there, correct? So at least these here, the conflicts at the Boolean search level are being prevented by 9 and 10. Whereas A8, it is avoiding the need to go to the theory solver again and again, so that you will not make some future decisions that are in conflict with the theory semantics. Yeah.
I see. So in general, the theory solver is sort of takes more time than say pure BCP provocation, right? Because it has to do
More
a lot
time
more.
than?
Yeah. Hello.
More time than what? Than
BCP itself. Like, so here we are sort of doing BCP and T solver calls alternatively. So the T solver calls will take a lot more time than the BCP, right?
yes, yes. I think the SAT solvers are, because they're engineered so well. Yes, you're right. SAT solver, I mean, both of them, SAT solver is NP complete too. And a lot of these decisions, even linear arithmetic inequality is NP complete as well. Okay. But if you want to derive these kinds of valid consequences, you will have to make repeated calls to your thing, right? So how did I say that you would generate, how do you know that you have to generate B3? For every literal that you have in here, as a result of making some decisions, you say, even if it is not conflicting with yet, I mean, it was conflicting once you made with B8, but just B5 and B1 itself was not conflicting by itself, and therefore I derived, so because B3, not B3 was derived, I did it. Anyway, so yeah, you're right that I think in complexity terms, both are equally hard, but SAT solvers are more mature than the thing, because it has a lot of learning and so on. But if for a new decision procedure, I would say that is to say that, I mean, if you there are two parts to your question. One is you're asking if theory solvers are generally more complex than just SAT solvers. Okay. Worst case complexity wise, if you look at linear arithmetic solver, that is also NP complete. Okay. And that is, the other one is NP complete as well. When you're combining these theories and then you're propagating equality, and then especially when you want to generate these things, so there you will have to do more work. Okay. Therefore, you may end up doing it. And of course, I mean, I would say answer yes to your question, but because CDCL, there's a lot of learning in SAT solvers, etc. So they're generally more efficient. But what was the motivation for your question? So you want to avoid, you're right, you want to avoid as much, as possible, calling theory solvers, okay? Because here, the theory solver is working, I mean, is used as a sub-process, correct? Therefore, you want to minimize your, your thing there, just like, yeah. So from that point of view, if you have generated B3 as a consequence of B5, B1, you might as well keep it, huh?
Yeah. That is, I was trying to understand the motivation, the general motivation.
That is the motivation, not because of whether SAT solver is more efficient than this one on, no. But see, if you did not store it, then future, when you make that decision, B5, B1, I mean, you're also doing some optimizations to make SAT solvers more efficient. Why would you want to add 9 and 10? Okay, because you add 9 and 10, that's what is making the search at the Boolean level also, well, no, you're right. Yeah, even this, because in this case, both these are theory conflicts. You're right. All of them are optimizing the number of times you will end up calling the theory solver. Correct.
Right. Okay.
Yeah, independently of whether SAT solvers are more efficient, theory solvers are more efficient. Okay, because here, I mean, you have to keep repeated calls for the theory solver. Now, every time you make partial assignments, you're trying to you're calling the theory solver. So make the best of it by learning from what you get from the theory solver. Yeah.
Yeah.
Okay, good. Anybody has anything? Okay, so if there are no more questions on this, I just want to open it if there are anybody that wants to bring anything about project. Otherwise, I know what but I'm urging not to take it easily. This is what happens when you extend something. There'll be another week, for which human nature is for you to put off till another deadline comes. But anyway, the deadline has been extended. You still want to discuss till 5 o'clock? We are here. If not, I will stop sharing.